Okay, so we have Poyntings. I did it again, sorry. And I told you we are going to be a bit speedy because I have lost 2 hours, which I cannot happen to compensate. So Poynting's vector in linear isotropic material. And then we said that the transmission there is a survey on the course page. Please fill that survey. I want to come here and we go through the survey together so that you understand what it is. We all understand how the course is moving. So we say that once we have this was our boundary, and then we have the vertical E, and we have the horizontal H, and they come and go through here. They still carry the energy. So when you have the H and E, or you could have drawn the H along here, and you use the right hand rule, the S is the Poynting vector. And we said that as this, when you combine the energy in the electric component and in the magnetic component, then you take this propagation to be carrying the energy. So the transmission of electric and magnetic fields through a medium implies transmission of energy. Since of course E and B, since E and B fields involve stored energy. You remember when we had the E is equal to half, was this the energy density UP? Yeah. So we said that we have some energy due to the electric component in electric fields. In electricity and magnetism, if you remember, we had that energy E is equal to what? Half Li squared something of the sort, which was the same as also, which should be the same as, I think you can say UH could be a half B dot H. So since E and B fields involve stored energy, then we also say the E cross B, the E cross H, which is equal to S, also has energy. And we said, of course, this is energy, the Poynting's vector is the same as energy, flux, if you remember, or energy per unit area. So let's consider a volume V. Consider a volume V. I think this is always used for velocity, so I will use the V. Consider the volume V enclosed by a surface, enclosed by a surface S. Take a material inside this surface, inside the surface S, or enclosed by, to be uniform, and isotropic, and to have permittivity, epsilon, and permeability mu. Of course, the rate of change of energy inside the surface S, is given by the rate at which the energy will change. Would have it as du dt, because I have Kali by Kali T the integral over the volume V, and then you have what I had here as the energy being a half, but of course that was energy density, but the energy was the same as integral over the volume V, that E the tau. Remember we had I think tau, but of course we said volume V, so it is V. So tau is where tau is the volume. And so we have D dot D, or D dot D, doesn't matter, that product is associative, plus D dot H. And then we have our tau, and this red covers everything. And then we shall say that this would be the same as that red would be U, the T would be the same as integral. We add the Kali by Kali inside, so we'll have integral inu Kali by Kali T plus Kali by Kali T dot H. This is being integrated over the volume d tau, but if we could state our Maxwell's equations. Pardon? Maxwell's equations. We got our divergence of B equals to rho. Then we have the one which we don't have an n equals to minus 0 also. But then 3 we have the curl of E V minus Kali B by Kali T for we have the curl of H equal to J Kali B Kali T. So you are talking about half. And then, we say that Kali D from equation 4, Kali D by Kali T is equal to curl of H minus J. And from equation 3, Kali B by Kali T is equal to minus the curl of E. This would imply that our du dt would equal to integral over the volume V. We substitute for Kali D by Kali T, which is the curl of H minus J. This all is done with E. And then that E tau minus integral over the V minus J. The minus J, I take J dot E tau. Now I subtract integral over volume V. The other part will be H dot this, so H dot the curl of E tau. I guess everything is okay. I've just substituted these ones in here. So I put this one in here, which became curl, because that product is distributive. If it is distributive, so this would be dotted with this, and also dotted with this, which gives this and that. The other part was the Kali B by Kali T was the curl of E minus, which is this minus here. H dot curl of E is the same as curl of E dot H, because that product is Amani. What is my name? Okay, so I ticked him and never ticked you. No, I got my. So, what does that mean? You stole it, or what is it?
I don't know. I think it's in what we are saying.
But I remember who brought two. Did you bring two? So how come you brought his and yours and his? But I remember somebody bringing two and telling me this is for so and so. I will come. Maybe you brought it, but you are confused. So using the vector identity, that the divergence of two cross product of two vectors E cross H is equal to, anyone who can read for us this identity or known as identities. This is equal to H that the curl of the first vector, then minus the second vector dotted with the curl of the first one. This is an identity. So the first one is H. Or whatever, whether first one or second one. So if we apply that identity, and you can guess where we want to put that identity, we have this H dot, the curl of E here, so we can replace it with the divergence of E cross H plus E dot, the curl of H. And then we achieve what we want. Okay, so then, when we put in our identity, we have our du dt being the same as minus integral vj dot e. What is the essence of a half anyway? What is the essence of a half? If you remember the superposition principle. Remember the superposition principle in electrostatics? What was the essence of a half? So this is d tau minus integral over the volume V, the divergence of the E cross H, tau. Using the divergence theorem on the last term, using the divergence theorem on the last term, or the second term, since there are only two, du dt is equal to having one issue with my notations. All along I'm having in here I have Khalif by Khalif. I'm not sure why, but I would make it total. I don't think I would have done any problem or any real thing. So using the divergence theorem on the last term, I'll get u dt being the same as minus integral over volume V. And then I have j dot a d tau minus integral. So I'm changing from the volume to a surface. So over the surface S, E cross H. And then that will be S or N roof. Yes. If the free charge density, within the volume V, is given by rho, and if the average velocity of the charge is V, which is a vector. Then we would have that the current density with which this charge will be moving, J, will be given by rho V. That's the formula. I have nothing to say about it. It's the charge density times the velocity at which the charge will be moving, then you will get the current density. And this would imply that our J, or say minus integral J dot E, the tau, we substitute for the J as we have gotten it here in terms of the velocity and the charge density. And this would be the same as minus integral over the volume V. We put in rho V, where rho, the V now is the velocity, so V. And this would be dotted with E. And then the tau. And this would be equal to, this would be the same as, let me put it here, minus integral over the volume V. And then we can dot the E and V and put the rho outside. So we have E dot V rho tau. Thus, we would have that the du dt is equal to minus integral over the volume V, which is different from the velocity V. And then we have E nu, E dot V, E dot V, rho d tau, and this you subtract off the other term, this term here which we introduced in after using the divergence theorem. And is minus integral over the surface S, E was H dot N dx, where minus integral over the volume V, E dot velocity V, rho d tau, represents the rate, of Joule heating, while you would touch a transmission cable in the TV and then you feel it's heating up in volume V. We have a few things to note. So note that when rho is equal to 0, note that when the charge is no charge, then the term tends to 0. Then the term tends to 0. Of course, when there is no charge, you wouldn't have any Joule heating, and you wouldn't be having anything moving around. While this other term, the other term equals integral over the surface S equals H dot MDS is the amount of energy flowing outwards of the surface. Outwards of the surface is, of course, you are having getting out along the normal, and and this should be per unit time. So the vector S where S is equal to the vector S. Should I put the vector here, or when I say vector S is enough? In Naruma, you have my other questionnaire, now I remember. Because I knew it was Kentaro and Manila and where is it? Huh? I should have, you seem to know. Whatever. So the vector S, which is equal to E cross H, I was thinking whoever was bringing back, so I know who did and who brought back. And I don't trust students. So S is equal to E cross H is called Poynting's. It's called Poynting's vector. And it represents the energy flow per unit area per unit second. Is it a unit second or per second? I think second is almost the smallest standard unit, so we can't say unit second. So per second at every point. So when I tell you to define the Poynting's vector, it is the energy per unit area, or the energy flow per unit area per unit time, or per second. If you talk of time, you say per unit time. But if you say per second, that's enough at every point. Along in a given medium as you are having transmission of electric magnetic field. So we have our right-handed system with our E, with our propagation vector, direction, and then you have S being along the K, and you have the H perpendicular to E, perpendicular to S, and also E being perpendicular to S. And of course, this energy flow per unit time, per unit area per second at every point is along the direction of propagation. This, it is directed, it means the Poynting's vector, it is directed along the direction of propagation. Along the direction of propagation. For complex fields, meaning for complex E and H, we put these fields, for example, for E, we put in our complex variables, which is E naught, R, and then we have exponential minus j omega t, which can be taken as E1 plus E2 plus J. So this is E1 plus J E2, which would be the representation of our E naught, and then we have our E minus J omega t. Remember, we we took our E naught as the amplitude. And now for our E naught is our complex, should I say complex amplitude. And then we can write it as the conjugate of our electric field would be the same as change the sign of the complex variable or the complex component. So this would be the same as E1 minus J, E2, and we have our exponential J omega T. Also, if we do the same for the other field, which is the H, we would have that our H naught R would be the same as, or exponential minus J omega T would be equal to, or maybe I should be nice, that H is equal to that. So which would be equal to H1 plus J, H2 into exponential minus J omega T. Thus, we would have our H conjugate, complex conjugate, being the same as H1 minus J, H2, exponential J, positive J, omega T. So we note that, of course, who can tell us what this one would be in full in terms of the cos and the sine? What would be E, which is equal to H naught exponential minus J omega T equal to in terms of the cos and the sine. How would we, what is this, what is EJ, what is EJ, E minus J omega T equal to? We have a J, so you shouldn't be fixated with that. Because we are dealing with electricity where we are prone to have I as the current, then we use J for the complex. For the complex? For the complex notation. So then we have J sine negative. So now when we multiply by this, we would have brought in the only thing as H, and so on, and the E's. So we have the real component. Otherwise, this would have implied that for E1 plus J E2 E J omega T would give rise to E1, then E minus J omega T plus J E2, then exponential minus J omega T, and then this would be the same as E1 cos omega T. So I can say E1 minus E2. Is that true? Cos omega T. Then the other one is what? It's not true. So I have to first put the cos omega T
Then this one, the other positive part will have the sign.
The positive part will have a sign.
Plus E2.
Anyway, I know you're just trying to waste my time. So let me do my business. So this is E1 cos omega t minus or plus? Minus J E1 plus JE2 then minus plus. Why? Yes. John, J do what?
Negative is positive.
It's positive. So J
Plus E just
so okay, plus sine E2 sine omega t. Okay, now you seem to be waking up. So I have this is real and this is real. These two are imaginary. So these count for the imaginary part, and these real parts are the ones which give us the physical. Remember that word? Yes. The physical component. So we have the real. We note that the real component of E is equal to E1 cos omega t plus E2 sin omega t. And if we do the same business for the H, we get that the real, actually this R should be nicely drawn, you know, like this. See, like that real, that's how it should be, but I can't really draw this all the time. So the real of H, this would be the same as just like up here, H1 cos omega t plus H2 sin omega t. Now the time average Poynting vector, the time averaged Poynting vector which we can write as is given by, we write it as S and put these two signs to show that it is an average. And if you remember in alternating currents, AC circuits in our electricity and magnetism, we got the, if you define the periodic function, ft, if any function ft is periodic, we gave a formula for it. And then we were able to find the average of the cosine, average value of the sine, average value of the cos 2 omega t, cosine 2 omega t, and also went ahead and looked for the average value of the square of these trigonometric ratios. That is the average value of the cos square omega t and the sine square omega. So if you can have that flashback, the formula for this would be the average value of the real of E crossed with the real value of H. And this would give rise to S being the same as a half. And of course, if you try to look for the real of E, there's a up there, and then you have the real of H, cross them, after crossing them, then you take their average value, which should give you E1 cross H1 plus a half E2 cross H2. Or we can write our Poynting vector, average Poynting vector S, as being the same as a half simply real of E cross H, where the E1 and E2 are components of E, H1 and H2 are components of H. We go further and try to recall what we did somewhere in the previous parts, where we were able to relate the propagation vector and the electric component in relation to the magnetic component. So recall that we said that H is related to the propagation vector and the propagation wave vector or wave propagation vector or wave number per se, and the electric field intensity by looking at the permeability of the medium and the frequency at which these fields are moving. And we said this is K cross. And if you remember, we ended up saying that K dot E and K dot H was equal to. And that's when we concluded that actually these are perpendicular to each other. Each perpendicular to the propagation vector. So this would imply that our S will be equal to 1 over 2 mu omega, then real of E cross H, and H is now K cross E. And then I have that this would be the same as 1 over 2 mu omega, the real component of, if you expand this, if you remember the vector cross to be the cross of another vector, you will get E dot conjugate. Then you have the vector K. This is sorry, here this is K, the vector mod. Remember the omega came in when we replaced the wave number, because K roof was equal to K vector over K, and then we came up with the K is equal to omega over what? Omega over. So these are correct. This is a vector minus, this is just an identity. This is an identity of expanding this using an identity. And this would be E dot K into E conjugate. But K dot E, we say it is equal to 0. So this would imply that our S would be equal to 1 over 2 mu omega, the real value of E dot E complex conjugate multiplied by the vector propagation vector k, and then I can close the brackets. If I go further, this would be the same as equaling to E naught squared E naught squared divided by 2 mu omega, and we have our k vector. So far, so good, but we know we can express this in terms of the phase velocity of the electric and the magnetic field, since we said these two have to be in phase. So the phase velocity Vp is equal to omega over k, which is the same as 1 over root epsilon mu, implying that our omega will be equal to k, omega will be equal to k over root epsilon mu. Remember when we said the phase velocity in free space would be c, and instead when we were in free space this was root E naught mu naught. And this would imply that our S, in terms of these new parameters we have brought in, would be the same as E naught squared divided by 2 mu, and then we have the reciprocal of omega, which was down here, which would be epsilon mu over k. And then that would be multiplied by the vector k. But the vector k over the magnitude of k would be equal to k root. So that means that if that is true, that k over k is equal to k root, it implies that our S would be equal to a half the root of epsilon over mu, and then multiplied by the E naught squared and our k root. So it is along this average Poynting's vector is still along the propagation. In the direction of propagation. And is when we know the permittivity, we know the permeability of the medium, and we know the amplitude of our field, then we can find the Poynting's vector. And even if we were given the electric amplitude, we can use the relationship here to find the magnetic field amplitude. Okay, so we need to recall that actually, in order to get to 2, our E naught divided by H naught was the same as the root of epsilon over mu, implying that our E naught amplitude is the same as, if we made it the subject, would be the same as root epsilon over mu multiplied by H naught squared, no, not squared. If I now want to bring in the H naught squared, how the average Poynting vector would relate to the amplitude of the magnetic field, then I would have that E naught squared will be equal to epsilon over mu H squared. Is that the case? I think on the recall I made a mistake. This should be the reciprocal. Am I getting hungry or tired? So this is mu of epsilon, and mu of epsilon. Because this is epsilon over mu, if you recall the expression. And of course, if that is the case, then our S, our average Poynting vector will be the same as a half E nu, the root of epsilon over mu, then multiplied by our mu of epsilon H naught. And therefore, our S, this is root epsilon, one roots go. So when one mu goes, it becomes root mu over epsilon. So this is a half root mu of epsilon H naught. This should be squared. H naught squared. Okay. So the only difference is about this ratio. For when we use the electric component, it is epsilon. So just take it. Permittivity is in electric. So that when permittivity is above, you are talking about the amplitude of the electric component. When it is the mu which is above, then you are talking about, I'm giving you a simple way of remembering these two relations of the averaged Poynting vector. So if you are given the amplitude of the wave, plane wave, and you are given the permeability and the permittivity, then you can find the average Poynting vector. So what is missing there? The K roof. K roof shows you that this is propagating in the direction of. So let's do an example. Let me see how many examples we gotta do. So this is example 1. And it says that a plane radio wave. Are we meeting after lunch? It is tomorrow. My head is fast forward. No, Wednesday we are meeting. Yesterday I just didn't pick the projector in time, but we were supposed to meet at 3 to 5. So tomorrow we will meet at 3 to 5. So a plane radio wave travels in the Z direction and is plane polarized with its electric vector, E, moving in the X direction. its frequency is 1 megahertz. The average power propagated by the wave is 20 watts per minute. The average power propagated. So when we say power, of course, power is energy per second. So when we now say the energy power propagated is 20 watts per meter square, already we are talking about watts per meter square will be the same as energy, the rate of energy flow. So this is already the Poynting power, or whatever you want to call it. So we want to determine the wavelength of the wave. The wavelength of the wave. To find the amplitudes of the vectors of the vector fields E and B. Example 2. Exercise 1. So exercise 2. Since you are seemingly complaining that I'm taking your time to do examples, so let me go for plan B. Exercise 2. A laser beam. A laser is what I was using to point at the screen the other time. That is the laser. So a laser beam, but you did that in the web optics. A laser beam has a diameter of 10 to the negative 3 meters. Calculate the amplitude. Calculate the amplitude of the magnetic flux density in the beam. In free space, if the power of the beam, is 1 watt. If you have time, we could do them. But since you just want to go eat, they are exercises. But don't worry, the answers are on Mwere. The notes are on Mwere, and you can find the answers